Okay, so this is a discussion on a small problem that I just saw. So, suppose you are given a list of numbers where every number either repeats three times. So let's say you are given a list like this: one, two, one, two, one, maybe zero, and then two. So every number either repeats three times, like one and two over here, or it occurs exactly once in the list. So you're given a list like this. Let's call this list as, I don't know, something, let's say A. What we want to do is create an order n algorithm where n is the length of this list. So create an order n algorithm which will traverse this list, and it will give us this unique number, and these numbers are all 32-bit numbers, so it's bounded. Now give it a try. Okay, I'm assuming that you're giving it a try. This is a very standard question which is usually done by just counting the number of times that a bit particularly repeats, and then taking its modulo with 3, and that helps you reconstruct the whole number. Now I want to do it slightly differently because I do not want to rely on actually storing the bits in memory like as integers, because that's a lot of space which is wasted, and obviously also leads to really bad runtime. So I want to do it with something much more efficient. So what my choice of algorithm would be something that relies on the ternary system. Why the ternary system? So here's the thing. Let's say you have a number which I'm writing in ternary. So it's something like 1 2 3. So 3 is not a digit in ternary, so you don't have that. So it's like 1 2 0 2 etc. So basically you have a list of numbers, right? So this is one number, and some other number is maybe like 1 0 2 1 whatever. The thing is, when you add a number, so not even add, when you just add the digits internally of a number three times, right, you'll just get 0, because the addition of digits is done modulo 3 automatically, right? So you get 0, and so basically for your 3k plus 1 numbers, only the one which is unique will survive, and everything else will just be reduced because it's modular arithmetic, so it just turns out to be 0. Now the problem is that computers aren't actually built in ternary, they are built in binary. So we'll have to build some sort of digital logic which will help us have ternary addition, right? Or addition of numbers modulo 3. All right, so here's what we'll do. Let's have so we are going to think of so so we are going to think of every bit. So once again, we'll represent numbers in binary, but then we'll add them up in modulo 3 fashion, right? And that way the numbers which occur three times, their bits will add up to 0, so they'll cancel. So your first number would be something like 1 0 1 0 0 0 whatever, then other one will be like 1 1, maybe 0 1, etc. And so when you add these up, you add it up in ternary, you say 1 plus 1 is 2, and 0 plus 1 is 1, 0, and etc. If you have to add something else to it, maybe something like this, then this 2 plus 1 is, so it should be 1 carried on, but we'll avoid carries completely. It will just be 0. So it's something like the XOR operation that you do for binary numbers, except that it also has this extra digit 2, right? So we'll have our two numbers which will represent basically an array of these ternary digits. I shouldn't say ternary digits. These are going to be just binary numbers, like it's ones or zeros, but then so it's something like this. Like let's say x1 is 0 0 0 0 0. For now I'm just taking five digits, so 5 bits is more like it, and then here it's like 0 0 0 0 0 as well. So this combined will represent one bit or digit or whatever in our base 3 system. So if it was a number like this, maybe it was a 1 over here, this represents 2. If it was 0 and 1 over here, this represents 1, etc. and this thing 1 and 1, this is invalid. You shouldn't ever have this. And so we want to do our operations in a way such that a situation like that never happens. So every time we encounter a new number which you want to add to this array of bits in base 3, you'll have to basically build a logic that you'll have y as something. So based on like x1, I don't know, let's say the third position of x1 and third position of x2 and third position of y, you can just use these individually to create a third position of x1 and x2 after this update, because x1 and x2 combined basically represent your number, right? Okay, so this is going to be easy. You have x1, x2 and y. So you could have 0 0 0 1 1 0 or 1 1. If y is 0 0 0 or 0, your x1 x2 after the update will just be 0 0 because y is 0 throughout. So here I'm saying y is 0. What I really mean is the particular bit of y that we are thinking about, that is 0, right? So these are not right now these are not arrays of bits, these are just bits themselves, so don't worry about that. Yeah, but I hope I'm getting through. Okay, then you'll just have once again 0 1 1 0, and over here it's a don't care, because we really don't care. You'll never have to see a thing like this. Similarly, you'll just have 0 0 0 1 1 0 1 1 1 1 1 1, and then based on that you'll have the update. So it's like 0 1, this is 1 0, this thing is 1 1, but then again 1 1 is just 0 0. There we go. This seems okay, right? And this is an invalid state, so once again you never see that. Sure. And with this you can have two k-maps for x1 and x2, and that will give you the logic that we're looking for. So we'll just have x1's k-map. So I'll draw it like this. It's y x1 x2 0 or 1. This thing is 0 0 0 1 1. It's not 1 0, sorry, it's 1 1 1 0. So alright, so this is going to be, so for x1 this is going to be 0 0 x1 0 1 x and 0. So you can just combine these two and get the thing. So in this case it's y x2 and not y x1. Cool. So that's our x1's updated bit. Similarly you can get one for x2, so we'll get it for x2 as well. So we'll delete all of this. Cool. So this will be 0 1 0 and x, and this will be 1 0 0, and once again don't care. So now you can use this and this. So your x2 will be this thing, it will be y x1 bar x2 bar, or this thing. So it's having your x2 and it's y 0, so not y and x2. So you have your logic for both of these. This is for x2, this thing is for x1. So I'll just clean this up real fast. Alright, cool. So here's our algorithm. We'll initialize x1 and x2 both as 0. So this will be 0. And remember, all of these are just base 32-bit numbers. So remember that. And now for y in our list, so a, what we'll do is just this thing. First we'll calculate this not y because it's an essential thing. So not y, that's going to be not y. Then you'll just have not x and not, because this is once again required, so not x1, that's not x1, not x2 is just that, not x2. And then you can create these things. So x1 will be this, it will be y, and so x2 or not y and x1. All right, and x2 will be this thing, so it will be y and not x1 and not x2, or you could have not y and x2. So there you go, that's your logic. So now after all of this is done, in the end you just have one particular number's bits, right? And although these are in ternary, they are in the end just going to be ones or zeros, because that's their values in the end. So because these are just ones and zeros, your most significant bit will be 0, since we are thinking of like 2 bits representing your ternary bits, right? And so x1 will be 0 throughout. What does this mean? That you just have to return x2, because that's your unique number that was in the list. So you just return x2. And this is your algorithm. This is the solution for the problem. All right, so this is an order n solution. It runs extremely fast. So this is straight from this site called LeetCode. It's, I think, called single number 2 or something. That's the problem name. You can try solving that. And yeah, this is it. So I'll see you guys in the next video.